Let's talk about what trajectory a charged particle follows in a uniform magnetic field. Now, first of all, we have to be aware of our convention to denote directions. If it's a perpendicular to plane direction, when the arrows point out of the paper, we show it with a single dot inside a circle here. So that means the arrows point out of the paper towards us. If the arrows point into the paper, then we have basically a circle with a cross in it. So this cross with the circle denotes the vector goes into the page. Now, when we put a charged particle with velocity v in a uniform magnetic field, so you can see that we have these crosses here, which shows that the magnetic field points into the page. If I follow my right hand rule, the right hand fingers point towards the velocity. If I curl them towards the magnetic field, which is into the page, I see that my thumb points in this direction. And since this force is always perpendicular to the velocity vector, that gives us this motion is, well, the trajectory that defines this type of motion, where the force always points perpendicular to the velocity vector, is uniform circular motion. So we can see that this particle, when it enters this region with uniform magnetic field into the page, will basically rotate on this circle with uniform circular motion. Its speed will not change because the force does not do any work, but its direction of the velocity changes and the force is radially inward. It's pointing towards the center of this circular path. So the force is always perpendicular to velocity and magnetic field, which gives us uniform circular motion. If the magnetic field points into the page and the charge is positive, that's the scenario that we have discussed here. Magnetic field points into the page, charge is positive. We have counterclockwise circular motion. If the magnetic field is pointing into the page but the charge is negative, remember, if the charge is negative, I have to use the opposite direction for the force, and that will basically tell me that this will end up giving me a circular trajectory. So a clockwise trajectory. So in this case, clockwise circular motion will result. If the magnetic field points out of the page, the charge is positive. If the magnetic field points out of the page, then that means the V cross B will give me a force that points in the opposite direction, and that will give me clockwise circular motion. If its Q is negative, once again, the sense of the circular motion will change. It will become counterclockwise circular motion. Okay, so if the velocity vector is perpendicular to the magnetic field vector, as I have shown in this example, velocity vector is perpendicular to the field vector. The field is pointing into the page, the velocity is in the plane of the page. What happens? So if the velocity is perpendicular to the magnetic field, then we will have the magnetic force QV cross B, QVB, because sine 90 is 1, and this will be equal to mass times the centripetal acceleration, and that is mass times the speed v squared divided by r, the radius of the circle. So we will see that the radius of the circle will be equal to mv over qb, because we will have one of the v's cancelling, mv over qb. So this v squared will be cancelling with this v, and we will have mv over qb. And the speed is ds dt, and which is equal to d dt over of r theta. So if you basically make an angular displacement by an amount theta here, we will see that if I have an angular displacement by an amount of theta here, the path length between these 2 points will be equal to r times theta. So that's going to be equal to delta s. So ds will be d of r and theta. Because r is constant, it comes out. So this is r d theta dt, which is equal to the angular speed. So this is omega multiplied with r. So omega, the angular speed, is the tangential speed v divided by r. V is 2 pi r divided by the period. So we can write omega as v divided by r will give us v divided by mv. So v's will cancel, divided by qb. So omega will be qb over m. That will be the angular speed of the uniform circular motion. The period is the total distance we travel, 2 pi r to complete the circle, divided by the speed v, or v is 2 pi r divided by the period. So this will be equal to 2 pi over omega, the angular speed, and that will be equal to 2m pi over qb. So we can calculate the period of this uniform circular motion. The angular frequency omega is known as the cyclotron frequency, and it's basically equal to v over r, which is qb over m, and the period is 2m pi over qb. Now, if we consider a different situation, if the charged particle enters the uniform magnetic field with a velocity at some arbitrary angle, not at 90 degrees angle as in this scenario. So if the velocity vector has a component that points into the page, for example, we will have a different path. The path is called a helix. So why is that? Because the component of the velocity vector that is perpendicular to the magnetic field will dictate a circular trajectory that's going to be the projection of the motion on this plane. And on the other hand, the component of the velocity which is parallel to the magnetic field will indicate we will have a translational motion. So as a result of this, we see that if the velocity vector makes an angle with respect to the magnetic field, we form this helical path. So the trajectory onto the YZ plane is a uniform circular motion, but in the I-hat direction here, for example, we have translation. So this is going to be a helix. B points in I-hat direction. The x component of the velocity is not zero, so there has to be translation on the x-axis. So in this case, we don't have only y and z components of the velocity, but x component as well. So that gives us a translation on the x-axis. Vy and vz components dictate uniform circular motion for the projection of the motion on the yz plane. Okay, so if we plot on the yz plane the projection of this motion, we get this uniform circular motion with radius r. If we plot the projection onto the yx and zx planes, what do we see? We see that the y component is increasing and decreasing, increasing and decreasing. So we have this sinusoidal path on the y-axis. And for the z component as well, we have the z component is increasing and decreasing, increasing and decreasing. So we will have also another sinusoidal path on the z plane. So whenever we see a minimum on the y component, for example, we will see a 0 on the z-plane. So you will see that when we have a minimum on the y-axis, so that's basically down here, we will have basically a 0 on the z-axis. So you can see that these two sinusoids are out of phase by 90 degrees. So it's projections of the helical motion on the yz plane that gives us these sinusoids for the y as a function of x and z as a function of x for the trajectory of this charged particle. Okay, so we have discussed motion of a charged particle in a uniform magnetic field in two cases. The first case, when the velocity vector is perpendicular to the uniform magnetic field, we obtain uniform circular motion. If the magnetic field points into the page, which is denoted by a cross, when the charge is positive, it's counterclockwise sense. When the charge is negative, it's clockwise sense. If the magnetic field points out of the page, then for positive charges clockwise, negative charges will give us counterclockwise sense for the circular motion. And when V is perpendicular to B, the magnitude of the force will be QVB sine 90, which is QEB, mass times centripetal acceleration. This gives us the radius mv over QB, and its speed, r d theta dt, is omega times r. Omega is the angular frequency or angular speed. It's v divided by r. It's qb over m, and the period is 2m pi over qb. If the velocity vector makes an angle with the magnetic field other than 90 degrees, then we have a combination of translations and uniform circular motion, which is described by a helix. So this helical motion basically tells us that the projection onto the YZ plane is uniform circular motion. The projection onto the YX and ZX planes will give us these sinusoidal motions. So we will have this translation along the x-axis.